Good evening, everyone. It's nice to be back here at Ahmedabad University. I think I was there during the COVID times back in 2021 or 2022. Today, I'll be talking on the mathematics of Ramanujan in general and how it has influenced various fields. It is still influencing various fields of mathematics and science. So let us just look at the brief timeline. Here's a photograph of Srinivasa Ramanujan. It's a passport photo. It's not something wherein he's wearing a coat. Actually, he's just wrapping around the bed sheet in a hospital in England. So it looks like it's a photo in coat. But he was very ill at that time when this photo was taken. And you can see the stamps here. So it's a passport photo of Ramanujan. There's a very nice quote due to Neville, a British mathematician. He says, Srinivasa Ramanujan was a mathematician so great that his name transcends jealousies. A few days back, I was reading about Ratan Tata when he passed away. And there was an article wherein it said Ratan Tata was invited by Narayan Murthy of Infosys to address the Infosys crowd. And he said, "We are your competitors. How did you invite me?" And then what Narayan Murthy said was, Jamshedji Tata, JRD Tata, Ratan Tata are names so great that all these things transcend, they are beyond jealousies. I mean, similar to what is written by Neville, that was what was quoted by Narayan Murthy. So anyway, we will see different flights of imagination of Ramanujan, incredible formulas and giant leaps of thinking over this talk. So a brief timeline of Ramanujan. He was born in Erode, Tamil Nadu in 1887, December 22, 1887. So his birthday is coming in month and a half. In 1903, he passed matriculation examination from Town High School, Kumbakonam. In 1904, joined Government Arts College, Kumbakonam. He was a very bright student until 10th grade. And then he was completely occupied by mathematics. So much so that he started neglecting every other subject except math. So he failed in 11th grade. So he was dropped out of Kumbakonam College in 1905. In 1906, he joined Pachayappa College. Again, he left without completing his studies. Again, he failed his 11th grade. 1911, he published his first paper on Bernoulli numbers. 1912, back then he was already married, and so he needed to support his family. So he got a job at Madras Port Trust. But you see, the people that he met in life, many a times the success depends upon whom you meet. Hello, hello. Can you hear me? Okay. Hello, hello. Yeah, so he met many nice people in his life. So the person who secured him job at Madras Port Trust, I think it was V. Ramaswamy Iyer, he told him that he doesn't need to do anything. He just can keep working on his mathematics. So on the back of the pages, on one-sided blank pages, he used to work mathematics at Port Trust. So in 1913, he wrote first letter to G.H. Hardy, but Hardy was not the first mathematician to whom he wrote the letters. The first two mathematicians whom he wrote were Hobson and Baker, both of whom did not reply at all. And then he tried sending it to G.H. Hardy, and Hardy, of course, replied, and rest is history, we know. In 1914, Hardy told Neville to go to India to bring Ramanujan to Cambridge. So Neville himself was a fellow of Trinity College. Uh, he met Ramanujan in Madras, convinced him to go to Cambridge, but Ramanujan's family was against him crossing the sea at that time. But as it goes, like how support is eventually obtained to a person, I mean, the talent doesn't go waste. So Ramanujan's mother saw in dream that his son is sitting among a crowd with all other Europeans. And that's when she felt that, okay, he should go to Cambridge. So he got the permission and he went to Cambridge. He was offered a scholarship from University of Madras as well, and he sailed for England on March 17, 1914. If you see, he completed his 10th in 1904. Then 10 years later, he is in England. And 6 years later, he's no more. And what has been done in between these 12, 13 years is amazing. It has kept mathematicians busy for more than a century now. So he was awarded BA degree by research from Cambridge University. He was hospitalized in 1917, became Fellow of Royal Society, returned to India, and health deteriorated, and he died on April 26, 1920. 1927 was the year when the collected papers of Ramanujan were published. Now let us see some aspects of Ramanujan's mathematics. After 1920, when he died, 56 years later, Ramanujan's lost notebook was found. And there is an interesting history of that, and which I'll come to. But let us look at what all fields Ramanujan touched. So mainly they are in number theory and analysis. So elliptic functions, theta functions, continued fractions, infinite series and integrals, Q series, or more generally, basic hypergeometric series, partition theory, special functions, Mach theta functions. This is only a glimpse of large number of areas that he has contributions in. So let me just touch upon some topics of his mathematics. So partition of a number n is a non-increasing sequence of positive numbers which sum to n. For example, you have 15. One way to write 15 is 5 plus 3 plus 2 plus 2 plus 3 ones. And we are writing them in a canonical way, which is non-increasing order, okay? So this way, we avoid those things whether we have 3 plus 5, because whenever you have 5 plus 3 or 3 plus 5, it's actually the same partition, okay? So this is one partition of 15. And likewise, there will be more ways to write 15. So one of them is 15 itself, right? So how many ways there are to write a partition of 15, or how many ways there are to write a 15? So those are the number of partitions of n, and P of n counts the total number of partitions of n. Now this is of course something which resides in additive number theory, right? You are actually having a number which is being written as sum of other numbers. But you have some really startling discoveries due to Ramanujan, which I'll come to. So let us just observe some first few values of P of n. P of 4 is 5. These are 5 ways of writing 4. P of 5, if you see, turns out to be 7. And P of 6 turns out to be 11. One can actually verify this. Again, it's an additive process. But what Ramanujan found out was some multiplicative properties of the partition function. And these are really, back in those days, very, very startling advances in partition theory. So what are those congruences? Why do I write only P of 4, P of 5, and P of 6? You'll see they are the first examples of these congruences, which I'll come back to. But one thing that we should be careful about is if we are having P of 6, it's already 11. I mean, between these numbers, we don't see much of a difference in their magnitude. But soon, if you go to P of 20, it will turn out to be a very big number. If you go to P of 200, you already see it's a 13-digit number. So if you have a class, if you have a unruly class, you can make them quiet by giving partition of, say, calculate all of the partitions of 20, and then keep them busy. Anyway, so How are these numbers calculated, or how are their properties studied? So basically in combinatorics, we have generating functions, which can lead us to the coefficients of that particular function to be the objects which we intend to study. So for example, the generating function of the partition function turns out to be this infinite product, 1 upon 1 minus q, 1 minus q square, 1 minus q cube, and so on. If we study this as a formal power series, then the questions of convergence are not taken into account. But if we want to study it as an infinite product coming from, say, analysis, then we need to have mod q less than 1. How is this derived? I won't go into the details of. However, this product at once gives us information about all of the coefficients which turn out to be the partition function. So let me show you one scene from The Man Who Knew Infinity, the movie that was made on Ramanujan. Ramanujan is sailing to England. There is a fellow Indian who says, Ramanujan looks dejected, right? And there's a fellow Indian who says 6,000 miles to England. Can you imagine? And he curtly replies, I have known larger numbers. Perhaps he's talking about the values of the partition functions. I mean, here is P of 50. Here is P of 100. Here is another scene from The Man Who Knew Infinity. This is one of my favorite scenes. So you can see G.H. Hardy here, or Jeremy Irons, who played the role of G.H. Hardy, and Percy McMahon. McMahon was a famous combinatorialist at Cambridge. And here is Ramanujan. McMahon was of the belief that partitions would be, at least in the movie, they have shown it, that McMahon is of the belief that partitions are to be done by hand. Like if I have to calculate all of the partitions of 4, I should do that by hand. Or any number that I have, I should try to do it by hand. And Hardy and Ramanujan are of the opinion that, okay, we can do asymptotic analysis on partition function and try to get partitions of large numbers, because otherwise it becomes very difficult to do by hand. So in the movie, it has been shown that McMahon is not believing them. And when they first meet, McMahon says they are to be done by hand. And these people are of the opinion that, no, you can do it by asymptotic analysis. And then they say, let us meet after 1 month. And how high do I have to go? That's what McMahon asks. And he said, P of 200. And then in the movie, after they meet after 1 month, you see that both have calculated this P of 200. And then you can see McMahon in awe as to how they came up with P of 200, exact same value as McMahon got by hand. And you can see G.H. Hardy smiling. Of course, in reality, it did not happen like that. Both McMahon as well as Ramanujan were very good friends. But you see in the movie, they have made a very terrible mistake. That's why I have actually put this. So here is a 9 and here is an 8. So it differs by a very large value. Actually, it's a 9, which is the correct thing. Perhaps while copying, they made an error. So the error was only within, I mean, it's a fractional part, right? By asymptotic analysis, whatever you get might be a fraction, not necessarily an integer, right? There should be a integer plus some fraction, and I mean, less than 1. And then you can just omit that because P of n is an integer. So then that will match with what McMahon had. Anyway, so Hardy and Ramanujan proved this asymptotic formula. P of n behaves like this. And that's why you see it growing very rapidly, because it's almost an exponential growth. Exponential function divided by this 4n root 3. Or rather, I would say e raised to some constant times root n, but still it grows exponentially. So McMahon, as I said, calculated the values of P of n up to n equal to 200. And the way McMahon wrote is very interesting. So he wrote P of 0 is equal to 1, P of 1, this is by convention. P of 2, P of 3,
P of 4, and then he drew a line. And then he did P of 5, P of 6, P of 7, P of 8, P of 9, and then he drew a line, and so on. And that's how he calculated up to P of 200. He gave that table to Hardy, who passed it on to Ramanujan. And Ramanujan observed that P of 4, P of 9, all these numbers look to be multiples of 5. Now you may say, okay, what's big deal in there? There was a line after P of 4. After P of 4, P of 9, and so on. So one can actually guess this. But he also found out that if you look at P of 5, then P of 12, and so on, these numbers are multiples of 7. If you look at P of 6, P of 17, P of 28, these are multiples of 11. I mean, he's talking about 3 arithmetic progressions, and he found out these congruences. Now the list was with McMahon, who prepared it, but he wasn't able to see the congruences. He passed it on to Hardy. Hardy wasn't able to see the congruences. Ramanujan actually found out these congruences just by observation, and then later on he proved the first 2 and announced in a paper that there is a proof of the third also that he found. But that's not what he stopped at. He went further to find some identity which Hardy calls as the most beautiful identity of Ramanujan, and that is a generating function for P of 5n plus 4. And if you see, this generating function has a 5 in front. So this congruence just follows trivially after you find out this particular thing. Okay, so P of 5n plus 4 is congruent to 0 mod 5. Now for P of 7n plus 5 also, he has found a generating function, which is a 7 times a Q product plus 49 times a Q product. So again, it's congruent to 0 mod 7. For 11, it was only found 3-4 years back, and it involves a heavy use of computer algebra. Anyway, so this is the infinite, actually they found an infinite asymptotic series for P of n, but the leading term of which is this. And here is what Hardy actually has to say. I mean, in between, I'll have some quotes by famous people on Ramanujan. Hardy says, I still say to myself when I'm depressed and find myself forced to listen to pompous and tiresome people, well, I have done one thing you could never have done, and that is to have collaborated with Littlewood and Ramanujan on something like equal terms. So that's the respect Hardy has for Ramanujan in particular. So when asked as to what his most important contribution in mathematics was, he said the discovery of Ramanujan. Later, Rademacher actually found a convergent infinite series representation for P of n. So P of n is equal to this particular thing times an infinite series, which involves this Bessel function I of the second kind, and what are called as Kloosterman sums. Note that P of n is such a simple object, but its analytic representation is involving Bessel functions, Kloosterman sums, and so on. So it is this formula which made George Andrews realize that this is the field of mathematics that he wants to go into. He was just amazed looking at this formula. But what we can say is that this is definitely an integer. Here is Freeman Dyson, a famous physicist. This is what he has to say on Ramanujan. Whenever I'm angry or depressed, I pull down the collected papers of Ramanujan from the shelf and take a quiet stroll in Ramanujan's garden. I recommend this therapy to all of you who suffer from headaches or jangled nerves. And Ramanujan's papers are not only a good therapy for headaches, they are also full of beautiful ideas which may help you to do more interesting mathematics. So Dyson's first paper came in 1944, and that was on these congruences and how to explain these congruences in a combinatorial fashion. His last paper, I think, came in 2012. So you see how many years he was active. He passed away in 2020, I guess, Freeman Dyson. Here is the movie, The Man Who Knew Infinity, which came in 2016. Professor Bruce Berndt is holding the slate of Ramanujan. And when I asked him, which photo of yours is your favorite? And he said, this is my favorite photo. So he said that Paul Ehrlich has passed on to us Hardy's personal ratings of mathematicians. Suppose that we rate mathematicians on the basis of pure talent on a scale from 0 to 100. Hardy gave himself a score of 20, Littlewood 30, Hilbert 80, and Ramanujan 100. Of course, Hardy was quite modest, but he knew Ramanujan's strengths, and his originality is what struck Hardy so much. So, as I said, in 1976, Ramanujan's lost notebook was found. It was not a notebook, and it was not lost in a way, because these pages were kept in Trinity College library. But they were hidden from the mathematical public from 1920 until 1976 in a way, because nobody knew about them. And George Andrews actually found them. And he said this interesting story. So how pure chance event actually leads us to something really incredible. So he was visiting some place in Europe. And back in those days, he said that if you directly go to Europe, it was not a good idea. If you go to England as a one stop in England and then go to Europe, then the prices would be epsilon. But if you go directly to Europe, the prices would be 1 over epsilon. That's how he puts it. So then he decided to go to England, and there were a few days in between. And he decided to visit Lucy Slater. Slater was a student of Hardy, and she had said that some efforts of Watson on Ramanujan's work were preserved in Trinity College Library, so you might want to take a look at it. And he went there, and he found these 139 pages in Ramanujan's handwriting. Andrews' thesis was on Ramanujan's mock theta functions. And so Andrews actually knew about Ramanujan's handwriting and everything. And he came to know immediately that this is the work of Ramanujan. And he saw that some of the pages in there were on mock theta functions. So he ran towards the librarian and he said that, I need a copy of this. And the person said, that will be £7. Will that be all right? He said, that would be fine. And then he said, in mind, I was ready to take a second mortgage on my house to get it. So this is the discovery of the lost notebook, and we have seen how much mathematics it has generated over the period of more than 50 years, and it is even generating. I'll come to a very recent thing that I'm working on, which has connections again to lost notebook. Okay, let us come to a beautiful modular type transformation in Ramanujan's lost notebook. So what I'm doing is I'm taking psi of x, which is the logarithmic derivative of gamma function, gamma dash of x over gamma of x. If you look at its asymptotic expansion, it starts with log x minus 1 by 2x plus the terms involving 1 by x square, 1 by x cube, and so on. So this is as x tends to infinity. So what I do is I take this and I subtract off the first two terms. So the first term will be minus log x, then it will be plus 2x. Now what I have here will be big O of 1 by x square, as I said, as x tends to infinity. So if I form an infinite series involving this particular function, it is an absolutely convergent series. Say, for example, I do summation n, I call this as, say, lambda of x. So if I take lambda of nx, then this will be big O of 1 over n square x square. So by summing this is an absolutely convergent series. So what Ramanujan is doing is, he is actually summing summation lambda n alpha, where alpha is one positive number, beta is another positive number with 1 over alpha, alpha times beta is 1. He is adding some residual terms to it, multiplying it by root alpha, and then he's saying that f of alpha is same as f of 1 by alpha. It's a beautiful formula. And he also says that it is also equal to this particular integral involving what is called as the completed Riemann zeta function. So the completed Riemann zeta function, I'll just define briefly. So the Riemann zeta function has a pole at s is equal to 1. It's a simple pole at S is equal to 1. So if we consider the functional equation of Riemann, which in itself is a very, very beautiful formula. It's a symmetric thing between S and 1 minus S. And if I take this whole thing, okay, now Riemann zeta function is known to have zeros at negative even integers. Gamma function is known to have poles at 0 and negative integers. So gamma S over 2 has poles at -2, -4, -6, so on. And 0, okay? But let me first concentrate on this. These get killed by the zeros of this. This is an entire function. The pole of gamma is still remaining, but if I multiply it by S, then this pole is killed by the 0 at S is equal to 0. But this still has a pole at S is equal to 1, and I can kill that by multiplying it by S minus 1, okay? And then let's put a 1/2 as a normalization factor. Then this will be an entire function of S, which I'm calling as C of S, okay? So this C of S, when I evaluate at S is equal to 1/2 plus IT, then what I get is this function C of T. So I'm taking C of T over 2, and then I'm forming this integral. Now, how suddenly did we get this integral? So I'll just tell you one quick thing about this. Suppose I'm able to prove that f of alpha equals this integral. How do I get f of alpha equal to f of beta? I just replace everywhere, I mean, in here and in here, the identity that I have proved, alpha by beta. Now, beta is 1 by alpha. So here, log 1 by alpha will give me minus log alpha, and cosine is an even function of t, even function of that angle. So I'll get back the same exact same integral. So on one side, I have f of alpha, but this f of beta, because I have replaced alpha by beta. But this, if I replace alpha by beta, I get the same thing. So I get f of alpha equal to f of beta. So this is a beautiful modular relation in Ramanujan's lost notebook. Now, what is so special about it? So let's fast forward and go to 1975. So instead of subtracting both the first two terms, if I subtract only the first term, what I get is psi of x minus log x, which is big O of 1 by x. So if I sum that infinite series, it is going to diverge because it is a harmonic series. But what I do is, in order to repair that, I divide by n. So I get big O of 1 by n square. Again, this is an absolutely convergent series. So this is a function which was studied by Herglotz and later by Don Zagier. Herglotz was a PhD supervisor of Emil Artin, by the way. So this function was studied in detail by Don Zagier, and it actually is turning up in explicit formula, Kronecker limit formula for real quadratic fields. And they satisfy these beautiful functional equations. Like this is a 3-term functional equation involving f at these 3 arguments. There is a 2-term functional equation. You see x and 1 by x. If I put instead of x alpha, then 1 by x would be beta, right? Alpha times beta is 1. So this is the sort of thing that Ramanujan was saying back in 1919 when he had written that formula in. So the first genesis of Herglotz type functions, not Herglotz function itself, but Herglotz type function is in Ramanujan's lost notebook, which was an interesting thing to note. And we found it only 2 years back. Okay. Another thing related to this same integral, this particular integral, Hardy says that it has properties similar to the one which Littlewood and I have used to prove that the second moment of the Riemann zeta function on the critical line, which is a big deal in analytic number theory, moments of the Riemann zeta function. So the second moment, because this is 2, is asymptotic 2. Actually, there is a typo in Hardy's writing. It should be just 2t log t. But Ramanujan's integral also gives this similar thing. And very recently, in 2024, there is a paper of Darcis and Hillian where they study polynomial moments. So not just mod of zeta half plus it square as you see here, but along with that, there is some gamma function square, mod of gamma function squared and t to the 2n. If you look at these, their starting point in getting the asymptotic formulas is this identity of Ramanujan. And again, it's something in Ramanujan's published paper this time, which really is useful for them in their study. One of the hallmarks of Ramanujan's mathematics is that it frequently generates further interesting mathematics, and this formula is no exception. This formula is as in the modular relation that I showed you. This is what George Andrews and Bruce Burnett have to say. And we too found this very true because we were able to work on some more generalized modular relations, myself and my PhD student. And that led us to a new generalization of Hurwitz's zeta function. And that Hurwitz zeta function generalization looks like this. So it looks quite complicated, but this double integral, when you let w tends to 0, this double integral actually reduces to the 1 over n plus a to the power s, which is the defining thing for the Hurwitz zeta function. Then we were able to actually work out the theory of this zeta function. So all of it has its genesis in that modular relation of Ramanujan that I was showing. But there are scores of such modular relations. So I'm going to mention only 2 of them. And one of them, I had already given a talk at Ahmedabad University 2 years back or 3 years back. So I won't go more on that. But this is that relation. And this is for odd zeta values. There is a formula of Ramanujan. The odd zeta values are quite mysterious quantities because the even zeta values can be written as they are actually equal to rational multiple of pi raised to 2n. Pi is a transcendental number, then all of these zeta 2n's are transcendental numbers. But nothing is known for zeta 2n plus 1. Even for the very first quantity, zeta 3, we only know that it is irrational. We don't know whether it is transcendental. And Ramanujan actually is giving a modular transformation. In fact, this particular formula encapsulates all modular properties of Eisenstein series on SL2Z, E4, E6, E2, all of those modular transformations are embedded in here. Not only of those, there are Eichler integrals as well, but let me not say more about that. Another thing is, if you look at non-holomorphic Eisenstein series, so here is one such non-holomorphic Eisenstein series. It satisfies, again, its Fourier expansion satisfies a beautiful symmetric formula. This was given by Ramanujan somewhere around 1919, 1920, and it was rediscovered by Australian mathematician Guinan back in 1955. So it involves these modified Bessel functions of the second kind. Ramanujan reaches his hands from his grave to snatch your theorems from you. This was a statement which was made by Bill Gosper at a centenary conference at UIUC in 1987. By that, he meant that many of the results which people think are new are found in lost notebook. This has happened a number of times. And this result of Guinan that I was talking, the Australian mathematician, is again the same thing. Like we found, I mean, not as in myself, but my supervisor found that this is in the lost notebook much before Guinan did in 1955. So here is Bill Gosper. He is at MIT, but in computer science. Now let me change gears and come to the last discovery, or one of the final discoveries of Ramanujan, something which has had a very great impact in physics, string theory, everywhere right now in the past 20 years or so. So in his last letter to Hardy, Ramanujan introduced a mock theta function as follows. It's a function f of a complex variable q, which is defined by q series of an Eulerian form. What do we mean by Eulerian form? Eulerian form means something wherein you have, say, q to n square or n square plus n by 2, things of those sort, and then Pochhammer symbols like that. Okay, this symbol, I mean, if I have a sub n, this is 1 minus a, 1 minus aq, 1 minus aq square, dot, 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 1 minus aq raised to n minus 1. It's a finite product. Okay, so things of that sort are called as Eulerian forms. So it satisfies these 3 properties. This is what Ramanujan said. Infinitely many roots of unity are exponential singularities. What do we mean by exponential singularities? So something like this. So, for example, if I look at this, then this has, there is some constant in front, which I don't remember, but it is exponential pi square by 15t plus something involving t. So as t tends to 0, and what is relation between q and t? Q is e raised to minus t. So as t tends to 0, that means q is approaching to root of unity, which is 1 from within, radially. So as t tends to 0 plus, it behaves like this. And as t tends to 0 plus, you have infinity, right? So it blows up. But this is called as the exponential singularity. So he's saying that at all roots of unity, you have exponential singularities. Then for every root of unity, xi, there will be a corresponding theta function. That means, by that he means a modular form, which will make that exponential singularity kind of, the impact of that exponential singularity will be lessened because f of q minus that modular form will be bounded. But he said that just one such modular form cannot kill all of those singularities. There should be various theta functions or various modular forms for every root of unity. So it's a kind of difficult function to gather. Then Ramanujan gave examples of mock theta functions of order 3, 5, 7. There are also mock theta functions of order 10 in Ramanujan's lost notebook, and I'll come back to that. But until now, nobody knows what is an order of a mock theta function. So in his letter in 1919, he has given these are of order 3, these are of order 5, these are of order 7, and so on. But no one knows what do we mean by order of a mock theta function, and it's still unanswered. So many people have worked on this, Andrews, Hickerson, Choi, and others. It was not until 2001 that people really understood what is going on. Sanders Weggers, he actually gave a theory in which the mock theta functions, all of the examples of Ramanujan, actually they can be put in a grand theory, and the modern definition of which says that the mock theta function is the holomorphic part of weight 1/2 harmonic weak mass form. And I'll not go into that, but now there is a huge theory, and this has found applications in black holes, string theory, various other things in physics. Like you have a lot of physicists also getting interested in the uh, harmonic weak mass form theory. But do Ramanujan's examples of what he called mock theta functions satisfy his own theory? I mean, his own definition, sorry. So that has been done very recently. They have shown that all of Ramanujan's examples satisfy his own definition of mock theta function, but that Ramanujan's definition is not equivalent to the modern definition, which is this modern definition. So what did Ramanujan have in mind? Is it that there is another theory of which the 17 examples, and this theory also has these 17 examples as a common ground, but that two theories are completely different? We don't know. Here are 4 10th order mock theta functions. Now, nobody knows what 10 here means, but they have been categorized as 10th order mock theta functions. So let me just say that there are 8 identities of Ramanujan for these 4 functions, relations between these 4 functions, 8 of them, 2 per page, so 4 pages of lost notebook. And those 4 pages have led to 4 very influential papers by Choi in the late 1990s, all in very top journals like Inventiones, Advances in Math, and all. And the proofs of these identities are extremely difficult, uses heavy computer algebra. Like some of them are these big quotients of eta functions and all, like that he needs. What did Ramanujan have back then, which helped him to get these relations. There was no computer concept, right, back then. So those methods are still missing. Later on, there are simpler proofs that have been obtained for 6 identities now. But there are 2 identities for which only choice proofs are the ones that we know. And these are this is one of them. So it's a relation between this phi and psi. And there is what is called as a Mordell integral, which is here. Only one proof is known due to choice. And that's a humongous proof. Of course, we are happy that this has been at least proved, but we don't know what Ramanujan's thinking was. Okay, let me also now discuss something really very elegant. These are called Rogers-Ramanujan functions, G and H. They are defined by these series, and they are equal to these products. Okay, so these identities are called as Rogers-Ramanujan identities. Why are they called as Rogers-Ramanujan identities? Because they were first discovered and proved by Rogers back in 1894. But nobody knew about Rogers' work until Ramanujan actually found it. So it so happened that somewhere around 1917, Ramanujan rediscovered it in 1913 before going to England, but he did not have a proof back then. But in 1917, he was going over the older issues of Proceedings of London Math Society, and he somehow saw Rogers' paper, and he was extremely delighted. If I were in the place of Ramanujan, I would probably be very, very dejected. Like, oh, something that I thought was my own formula has been already proved 20 years back. But that's the greatness of Ramanujan, that he was extremely happy that what he was thinking, that this formula must be true, has already been proved. So this is indeed true. So he came running with that volume of Proceedings of London Math Society, and then he showed Hardy. Hardy, see, these formulas are true. Then Ramanujan himself actually proved these formulas in a different way. That's the history. And then Rogers, all of a sudden, became very famous. Yeah, exactly. Yes. So, yeah, right. So when Ramanujan found his own proof, at the same time, Rogers found there was a communication between Rogers and Ramanujan. Rogers found a much simplified proof of his identities. And then Hardy decided to have both papers of Rogers and Ramanujan published together side by side. And but Rogers rose to fame overnight because of these identities when Ramanujan rediscovered them. Anyway, if I call this Q as e raised to 2 pi I z, then if I multiply this G and H by these powers, then they turn out to be modular functions. So they satisfy modular transformations. And if I, this is something coming to the continued fraction, but the simplest continued fraction that we see in school is this. And we are very, very happy to once somebody knows it for the first time, he tries to ask somebody, can you prove this? Okay, then what do? You call this as x, you take the reciprocal, then it is 1 plus x, and then you solve the quadratic, you take the positive root, and that turns out to be this. But there is a lot more that is going on with regards to the convergence of this particular thing. Why is it convergent? Okay, so Ramanujan generalized this continued fraction. Again, Rogers also did this. So instead of 1 here, I'm putting q, q square, q cube, and so on. And then here, I'm multiplying that by q over 5. Why is this q over 5 important? Because it is coming in modular forms. Suppose I divide this by this, I'll get q to the 12 over 60, which is that 1 over 5. And if I divide h over g and use these formulas, this is what I get. So this continued fraction is this. When my supervisor said that he was writing a whole chapter on continued fractions, for which this is the notation, right? Because it is a compact notation rather than writing 1 upon 1 plus 1 upon 1 plus, which will occupy quite a bit of lines. This is a compact notation, 1 plus 1 upon 1 plus like this, to write it in the bottom. And he said everything was typeset and then sent to Springer. And the copy editor there thought that, oh, this guy doesn't know where that plus sign should be. So he put all of those plus signs here. And he said that he had to redo all of these 50 or 70 pages. So anyway, um, these are the Rogers Ramanujan identities, which have a very beautiful combinatorial representation. What is that combinatorial representation? On the right-hand side, we know that this is the generating function of partitions, which are having parts which are congruent to 1 mod 5 or 4 mod 5. But on the left-hand side, it's generating function of partitions into parts which differ by at least 2. I'm not going into the details, but you can see that both enumerate to the same thing. If you look at partitions into parts which differ by at least 2, and the partitions of the same integer into parts which are congruent to 1 or 4 mod 5, both are always the same. So that is what is the combinatorial interpretation of this identity, and similarly one can give for this. So Ramanujan actually evaluated those continued fractions at certain values, like this continued fraction at e to the minus 2 pi gives you this. And this was in the first letter to Hardy, for which Hardy had this to say. These formulas defeated me completely. I had never seen anything in the least like them before. A single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true, because if they were not true, no one would have had the imagination to invent them. Where are Rogers Ramanujan identities turning up in mathematics? Lie algebras, statistical mechanics, partition theory, modular forms, algebraic geometry, K theory, conformal field theory, group theory, Kac-Moody, Virasoro vortex, double affine Hecke algebras, knot theory, orthogonal polynomials, probability, transcendental number theory. You name a field and Rogers Ramanujan identity. Just 2 weeks back, there was an article in Quanta magazine where some identity of Ramanujan on these Rogers Ramanujan identities have turned up in combinatorial commutative algebras in a work of one Lebanese French mathematician, Hussein Murtada. So now I told you that I would be talking about, how much time do I have? 10 more minutes, okay. So I told you that there is something very recent that I was working on. It's this formula. It's a multi-parameter identity, A, B, C. A is a non-zero complex number, B can be any complex number. Mod Q is, of course, less than 1. What Ramanujan is saying is that this series times this series plus this series times this series is a theta function minus this. What's so great about this? I mean, it just looks to be something very complicated in the first look. Now, there is one identity related to this on the next slide, about which there is a quote of George Andrews when he wrote a preface to The Lost Notebook, which was published in 1987. This is what Andrews says. This sort of identity, when I say this identity, it is the one on the next page. This sort of identity has always appeared to me to lie totally within the realms of modular functions and to be completely resistant to Q-series generalizations. One of the greatest shocks I got from the Lost Notebook was the following assertion. This following assertion meaning this. So this gave a shock to George Andrews as to something like this is also true. What is so special about this identity? So let me say that if I let A equal to B equal to 1 in this identity, okay, so I'm getting this Q to the n square upon Q sub n, then Q to the n square by 4 upon Q sub n. A and B both are 1. Then summation Q to the m square plus m upon Q sub m, and Q to the n plus 1 whole square by 4 upon Q sub n is equal to 1 upon Q sub infinity summation n equal to minus infinity to infinity Q raised to n square by 4. That 1 minus b kills this term. This function we know what it is. It's the Rogers-Ramanujan function g. This function is the Rogers-Ramanujan function h. So what is going on? So if I multiply, if I replace q by q raised to 4 here, so the base also becomes q raised to 4. This becomes q raised to n square. Here I get q raised to 4. Similarly here. And here, and if I multiply both sides by this minus q square sub infinity, when I say something sub infinity, I'm just having this thing run forever, like an infinite product, okay? So if I multiply by this q product, minus q square sub infinity, then there are two identities of Rogers, like this times this is g of q. This is proved by Rogers. And similarly, I'm multiplying by this here and by here. This times this. You see, there will be an n square plus 2n plus 1. So that plus 1 I'm putting here. So this times this again is h of q. But what is this? This is g of q to the 4. And what is this? By definition, this is h of q to the 4. So what we get is this identity of Ramanujan. There are 40 such identities that he gave in the Lost Notebook. And what Andrews said was, this always has appeared to him to be within the realm of modular functions. Because you see, this is a modular identity, q getting related to q raised to 4. And what Ramanujan is doing is that this actually has an extension in terms of series. So this is beyond the modular forms that he has discovered. Very recently, in fact, so my student and I are working on a project related to this, and probably by day after tomorrow, we are planning to submit this. One is, we have generalized this identity in a different way, but one is left to wonder, how does one come up with such a thing? So only 2 days back or 3 days back at midnight, I found out one perspective of how Ramanujan may have discovered this. And that is asymptotic analysis. If you do, say I put b equal to 1, okay? Then if you calculate how this behaves as q tends to 1, how this behaves as q tends to 1, add the two, that is exactly the same asymptotic that you get for here. So asymptotically, this can be seen, and perhaps that led Ramanujan to see whether this is true in general for all mod q less than 1, and that's how he may have discovered this identity. Anyway, let me, because there is not much time, let me skip this part. Okay, if one likes integrals, then here is one integral on page 51. Integrals of infinite products, written in terms of elliptic integrals, incomplete elliptic integrals. There are no results of this kind available in the literature, other than Ramanujan, of course. So the taxi cab number, everybody knows that story, right? 1729. So Ken Ono and his student, Sara, they showed that Ramanujan had discovered 1729 K3 surface. It's some compact, smooth manifold. I don't know much about that, but it's this K3 surface with Picard number 18. So you see another area where some identities of Ramanujan, because people think that Ramanujan suddenly thought of that thing that, oh, 1729 is 12 cube plus 1 cube or 10 cube plus 9 cube. No, you see this page on the last notebook. I mean, perhaps this is not very clear, but he has actually had something more general, of which he's writing here 9 cube plus 10 cube and 12 cube plus 1. So it was that page on the last notebook that Ono and Sara, they both studied, and they found connections with something involving manifolds. So Freeman Dyson said, That was the wonderful thing about Ramanujan. He discovered so much and yet left so much more in his garden for other people to discover. The impact has only increased in recent years, but most of the results, almost all, I would say, if not all of the results have been proved, but we have been starting to understand them. I mean, they have been just proved. How did he think? That is a different thing. So Professor Bunt notes, the challenge is to ascertain Ramanujan's thinking and motivation and to properly place his work within contemporary mathematics. So this is probably uh, has just started. There is no doubt that his legacy will be appreciated as long as mathematics is. So here is the house of Ramanujan before it was renovated. Now this is a place of national significance in Kumbakonam. This is the place. Here is the bed. Here is the porch on which he used to sit, watch his friends play outside, and do mathematics. Here is Ramanujan when he got his degree. Here is Ramanujan with his other Indian friends in Cambridge at that time. Ramanujan's wife. She lived up to 1992. So many of the people who work on Ramanujan's mathematics, for example, Bruce Berndt, George Andrews, all of them have met Ramanujan's wife in person. Here is their adopted son. Here is the well at the back of Ramanujan's home. Thank you.